Where did everything around us, from the smallest things to the greatest, truly begin? When we leisurely cast our gaze in all directions into the vast and silent expanse of the universe, we see countless stars sparkling like diamonds, distant galaxies drifting quietly, and clouds of gas and dust floating adrift in the void. In that silence, there are also delicate streams of electrified gas and invisible bands of radiation silently spreading. These bands of radiation range from warm infrared rays to the visible light our human eyes can perceive, and even energetic cosmic gamma rays piercing through space. Our universe, at any time and any place, is always filled with matter and energy, no matter where we look or how we try to perceive it. It's only natural that an assumption arises in our minds that all these wonderful and vibrant things must have had an origin, some starting point in the distant past. If you yearn for the answer to the greatest question about the origin of all things, you must learn to ask the vast universe itself and listen to what it whispers through signals from the past. Welcome to the realm of reality, where mysteries are gradually unveiled. Today, we will embark on an extraordinary journey together, a journey back in time to find the starting point of the entire universe. How was our universe created? How could a tiny point become the seemingly infinite space we reverently behold today? And then, what will really happen when our universe comes to an end, billions of years from now? Scientists have grappled with these grand narrative questions since the dawn of civilization, and their answers have forged theories that are strange, magnificent, yet also fascinating. Ever since the Big Bang, a pivotal event that many believe marks neither the beginning nor the absolute end of the universe, we have been tirelessly searching for the most complete explanation for the formation of this world. Through countless generations and different civilizations, the curiosity about the origin of the universe remains as strong as it was thousands of years ago. Ancient civilizations, from the Chinese, Mayans, Arabs, Greeks, to the Egyptians, all held the belief that a supreme power, a great creator, brought everything into existence from nothingness. Although the theories and views of our ancestors on how the world was formed varied due to cultural characteristics, they often shared a common belief that the heavens, the underworld, and our beloved Earth were at the center of all existence. Subsequently, the geocentric model was officially born. Ancient Greek philosophers and scientists argued that our Earth was roughly spherical, not an infinite flat plane. They quietly observed the sparkling stars in the night sky and a few celestial bodies moving around our planet. Later, as knowledge expanded, the heliocentric model was formed, explaining that Earth and the other planets actually revolve around the Sun, and it is the Sun that is the central entity of our system. According to that view, other stars were believed to be fixed at an incredibly vast distance. It took many long years after that, about 2,000 years, for the astronomer Kepler to present his complete heliocentric theory, and this revolutionary theory was only widely recognized after his death. The universe includes everything you can think of, from lush green nature, the vast ocean with its murmuring waves, the human world with its myriad emotions, and even our solar system. According to profound studies of the cosmos and modern evolutionary theories, the Big Bang theory is currently the most widely accepted theory in the scientific community. This doctrine is based on a fundamental principle that nothing is spontaneously born from nothingness. For something to exist, there must be pre-existing matter or a core component. So, what really happened in that extremely brief initial moment to create such an enormous amount of matter? The ultimate cause of the Big Bang and the true origin of that matter remain, to this day, the greatest mystery for all of humanity. We still do not know with absolute certainty how our universe formed, or if something mysterious existed even before the Big Bang. However, physicists are working tirelessly day and night to find an answer about the initial quantum state of the entire universe. They strive to provide a meaningful explanation for the question of how something could exist from the realm of non-existence. All efforts to achieve this are still highly speculative and hypothetical. Some have invoked supernatural forces, like a great designer who drew the map of the cosmos. But alongside that, there are other plausible answers belonging to the realm of pure physics that we are gradually discovering. These scientific answers include the multiverse theory, which is made up of countless parallel universes existing side by side, or cyclical models of the universe where the world undergoes continuous loops of birth and rebirth with no end. Sir Roger Penrose, the brilliant physicist who was honored with the Nobel Prize in 2020, proposed a fascinating but controversial idea of a conformally cyclic universe. Roger Penrose was inspired by an interesting mathematical link between the incredibly hot, dense, and tiny state of the universe at the time of the Big Bang and its extremely cold, empty, and infinitely expanding state in the far distant future, trillions of years from now. His bold theory explains that these seemingly opposite states become mathematically identical when they reach the ultimate limits of space and time. Though it may sound unbelievable and like a fantasy story, all the matter in our universe could have truly originated from a complete absence of matter. From this scientific perspective, the Big Bang began from almost nothing. However, based on the most precise scientific calculations, our universe began its journey about 13.8 billion years ago. Although the name Big Bang might suggest a fierce, fiery explosion, it was not actually an explosion within space, but rather the sudden appearance of space itself, everywhere at once. Everything in the universe was then compressed into an extremely tiny point called a singularity. It was a point of infinite temperature and density about 13.8 billion years ago. That microscopic speck of dust is the source of everything in the universe today, the root of all elementary particles, atoms, and every type of matter that constitutes your body, as well as the stars. This is the first known era of the universe, also known as the Planck era or the Planck epoch. This period was so early that it transcends the limits of our best human understanding of the current laws of physics. This wondrous interval took place only about 1/10,000,000th of a billionth of a second after the Big Bang. At this extremely short moment, quantum fluctuations began to strongly affect both space and time. Typically, physicists handle general relativity, which operates on a vast cosmic scale, and quantum mechanics, which governs the microscopic world of tiny particles independently. But to truly understand the Planck scale, we need a complete theory of quantum gravity to unify these two great doctrines into a single, common voice. Despite countless, relentless efforts, such as the construction of loop quantum gravity or the enchanting string theory, humanity has yet to achieve a perfect and complete theory of quantum gravity. In that strange world, the ordinary space and time we are so familiar with are often seen as emergent phenomena that arise randomly, like small ripples on the surface of a deep and mysterious ocean. Because we are creatures of the large macroscopic world, when we reach the subatomic level, space and time seem to become meaningless and lose their familiar form. What we experience daily is actually just the end result of complex quantum processes operating silently at a much deeper level. There, we can no longer rely on our common understanding of the relationship between cause and effect, because in the distant Planck era, all of our standard concepts of space and time were completely broken. The brilliant physicist Max Planck devised a unique system of measurement in the late 1890s, hoping to express the laws of physics in a simpler, more fundamental way. These special Planck units can be calculated using only 5 unchanging natural constants, such as the gravitational constant and the speed of light in a vacuum. Scientists even believe that we could use these units as a common language to communicate with extraterrestrial civilizations from the distant Alpha Centauri star system. These Planck units consist of 5 fundamental quantities: length, temperature, mass, charge, and time. Take a quiet moment to think about the tiny Planck length unit. For comparison, a proton, which is already incredibly small, is still about 100 million times larger than this Planck length. To help you visualize this in your imagination, if we could magnify a proton to the enormous size of the entire observable universe, the Planck length would then be equivalent to the distance from Tokyo to Chicago, about 10,140 kilometers. A continuous 14-hour flight might be a long and tiring journey for you, but to the vast and immense universe, it is completely tiny and insignificant. Surprisingly, we have discovered that the limit of the Planck scale is also the final limit where our current laws of physics can operate normally. In the Planck era, our universe was so small that every law of physics humanity has ever known was broken and rendered invalid. To delve even deeper into the primordial past, we will certainly need a completely new scientific language that we are still searching for. Although we cannot directly observe or record what truly happened at the subatomic Planck level, scientists can predict that at this enormous and dense energy level, the 4 fundamental forces of nature — gravity, electromagnetism, the weak nuclear force, and the strong nuclear force — finally merged and combined to form a single, great superforce. Fantastical phenomena such as superstrings and quantum gravity may have been the dominant factors at this Planck energy scale. We need a newer theory of physics to understand anything beyond this tiny scale. The period of time immediately after the Big Bang is known as the Planck epoch. It began at absolute zero and ended 10 to the power of negative 43 seconds later. That extremely short moment is 1 Planck time. We are completely unable to use any of today's modern technology to measure the length of this moment, as it is so incredibly small and fleeting. These numbers truly exceed the full comprehension of the human mind. At that time, there was no such thing as primordial matter, because the entire universe was created in an extremely hot condition. It was so hot that everything existed only in the form of pure, brilliant energy. The universe then had an astonishing temperature of about 100 million degrees, equivalent to 10 to the power of 34 Kelvin, and it was about 100 million times smaller than a proton at the beginning of the Planck epoch. To give you a more concrete and relatable concept, this is the microscopic size of an atom. The typical radius of an atom is only about 0.1 nanometers. A nanometer is just 1/1000th of a meter. Atoms are already extremely light and small, and they are made up of even smaller subatomic particles like protons, neutrons, and electrons. These particles are even tinier and lighter than a complete atom. The Big Bang gave birth to the universe, and since then, the universe has continued to expand until now. However, one strange thing is that time and space did not really exist until the universe reached the size of the Planck distance. Space was then breathtakingly compressed, but time was still an ill-defined quantity. According to string theory, our universe had up to 10 spatial dimensions during the Planck epoch, but then 6 of them collapsed, leaving only the 4 that we perceive today. One way for you to visualize these 6 additional spatial dimensions is to imagine them as microscopic spheres, delicately hidden in the gaps between fundamental particles, existing alongside the 4 large dimensions and 6 other microscopic ones. The best way for us to let our minds wander and envision the universe during the Planck epoch is to imagine a quantum carpet woven from 10 spatial dimensions. That fantastical carpet contained countless microscopic black holes the size of the Planck scale, which were constantly being formed and then ceaselessly destroyed, creating a chaotic dance with no clear cause or specific effect. However, the extremely unpredictable and volatile state of the Planck epoch ended after only about 10 to the power of negative 43 seconds, a time so brief that our minds cannot possibly imagine it. At that point, the universe gradually cooled and began a process of vigorous development, signaling the beginning of a completely new era in the history of all things. For a very long time after that, the universe did not appear or operate in the same way we see it today. However, as the timeline moved forward, our existing scientific theories at least had a chance to partially explain what was actually happening. There are four fundamental forces that quietly govern and influence every small activity in our daily lives. They are gravity, the weak nuclear force, electromagnetism, and the strong nuclear force. From you casually playing basketball, to humans launching a spacecraft into the vastness of space, to a simple act like sticking a small magnet on the refrigerator door, all of it is happening under the control and influence of these forces. Every known interaction in the scientific world, from the smallest particles that make up atoms to distant giant galaxies, as well as the natural phenomena we encounter every day, is caused by these four forces. They brilliantly explain how galaxies move rhythmically in space, how chemicals react magically in a laboratory, the stable structure of atomic nuclei, and why radioactive decay occurs naturally. These forces also help us understand the true meaning of common concepts like friction or the normal force that we experience all the time. First, let's talk about gravity, a force you surely know very well and feel every day, as it is what keeps your feet on the ground and causes all things to tend to return to Mother Earth's embrace. Gravity is essentially the attractive force between any two objects that have mass or energy. It is silently present when you drop a small stone from a high bridge, when a planet quietly orbits its host star, or when the gentle moon pulls the undulating tides in the vast ocean. Among the fundamental forces of nature, gravity is perhaps the most recognizable and intuitive for us humans. Yet it is also one of the most mysterious and difficult to explain for brilliant scientists. The concept of gravity was first introduced by the physicist Isaac Newton. It is often told that he came up with this great idea while sitting quietly and observing an apple fall from a tree. He defined gravity as the physical attraction between two objects pulling toward each other. Centuries later, the genius Albert Einstein proposed a completely different and revolutionary perspective. Through his general theory of relativity, he argued that gravity is not exactly a conventional attractive force as we think of it, but rather the result of space-time being curved by mass. Try to imagine a heavy ball placed on a taut trampoline. The ball's weight will deform the trampoline, creating a depression and causing smaller objects nearby to automatically roll toward the center. The gravity of a massive object in space works in a similar way. Although gravity is the invisible string that holds planets, stars, solar systems, and even distant galaxies tightly together, it turns out to be the weakest of the four fundamental forces, especially at the tiny scale of atoms and molecules. Take a second to think about it. The act of you gently lifting a ball off the ground, lifting your foot to walk, or jumping high are all actions against the gravitational pull of the entire massive planet Earth. At the microscopic level, gravity has very little influence compared to the strength of the other forces. Next, let's learn about the weak nuclear force. While other forces tend to bind things together into a whole, the weak nuclear force plays a more significant role in causing things to gradually fall apart or decay over time. Although it only acts over extremely short distances, the weak nuclear force is still much stronger than gravity. It is an essential subatomic factor in the creation of chemical elements and is the eternal energy source for the stars that shine brightly in the dark night. Most of the natural radiation that exists in the vast universe is also caused by this very force. Although it bears the name weak force within the confines of a nucleus, it is actually about 10 to the power of 25 times stronger than gravity. It's called the weak force simply because its strength is still far less than that of the strong nuclear force, which we will discuss later. This force is responsible for the phenomenon of beta decay within the nucleus. The nuclear fusion reactions that are the immense energy source of the Sun, providing warmth and life to all species on Earth, are entirely dependent on this weak nuclear force. This is also the reason why archaeologists can use the carbon-14 isotope to accurately determine the age of ancient bones or artifacts that have existed for thousands of years. Thanks to the predictable decay rate of protons and neutrons, scientists can read the story of the lifespan of objects from the distant past. The third fundamental force is the electromagnetic force. This force works tirelessly between electrically charged particles, such as negatively charged electrons and positively charged protons. In science, we also refer to this as the Lorentz force law. A simple yet enduring rule is that like charges repel each other, while opposite charges attract each other fiercely. The magnitude of this force increases proportionally with the magnitude of the charges, and, like gravity, it can be felt from an infinite distance, although its strength becomes extremely small at very great distances. True to its name, the electromagnetic force consists of two inseparable parts: the magnetic force and the electric force. Initially, scientists used to distinguish clearly between these two types of forces, but they later discovered that they are in fact two faces of the same single entity. The electric component acts between stationary or moving charged particles to create a vast field of interaction. As soon as these particles begin to move, the magnetic component comes into play and creates a magnetic field around them. Therefore, when electrons rush through a wire to charge the battery of a computer, phone, or turn on a television, that very wire becomes magnetic. This energy exchange process occurs through the interaction of massless force-carrying particles, which we know as light particles or photons. The electromagnetic force is also the underlying cause of familiar phenomena we often see, such as the elasticity of a rubber band, the friction that helps us walk without slipping, and the force that allows solid objects to maintain a specific shape. It also creates the magical drag that birds or airplanes feel as they spread their wings in the high sky. For example, the normal force that keeps a book resting quietly on a table instead of being pulled straight down by gravity is, in fact, the result of the electrons in the atoms of the table's surface, silently repelling the electrons in the atoms of the book, preventing them from passing through each other. The final and most powerful force in all of nature is the strong nuclear force. This force is about 6 trillion times stronger than gravity. Imagine that, as the number 6 followed by 39 zeros. The strong nuclear force acts as a great glue that binds the fundamental building blocks of matter to create larger structures. Protons and neutrons are made up of tiny particles called quarks, and it is the strong nuclear force that keeps these quarks, as well as the protons and neutrons, tightly bound together inside the tiny atomic nucleus. However, this powerful force only takes effect when subatomic particles are extremely close to each other, equivalent to the microscopic diameter of a proton. This force is transmitted by massless particles called gluons. A small part of this force, which scientists call the residual strong force, has the crucial task of overcoming the electromagnetic repulsion between positively charged protons, keeping them stable and harmonious within the nucleus of an atom. Thanks to the strong nuclear force, matter can exist stably, creating the world and ourselves. In the flow of knowledge, physicists achieved resounding success by creating the grand unified theory to harmoniously combine the electromagnetic and weak nuclear forces. Then, at the beginning of the Grand Unification Epoch, that is, around 10 to the minus 38th seconds after the Big Bang, the strong nuclear force also began to separate from the other forces. This landmark separation released an enormous and terrifying amount of energy, causing the universe to expand extremely rapidly and intensely. Just imagine, in a brief span of 10 to the minus 32nd seconds, the universe expanded by a factor of 10 to the power of 35. This brief but momentous period is known to scientists as inflation or cosmic inflation. In the blink of an eye, the universe went from an incredibly small state to the size of a grape. However, you should note that this inflation theory only refers to the observable universe, not the entire, vast, boundless universe. The assumption of this exponential growth spurt has helped scientists solve two of the most perplexing problems: the horizon problem and the flatness problem of the universe. When you quietly observe the universe, you'll basically see that everything appears to be similar no matter which direction you look. The temperature of the cosmic microwave background radiation is nearly identical in every direction with incredible precision. If we think about it carefully, this shouldn't be the case, because light takes time to travel. When you look deep into space, you are actually looking back into the distant past. There is an observational limit in every direction of about 14 billion light years. Suppose you look in direction A, 14 billion light years away, and then you look in the opposite direction B, also 14 billion light years away. These 2 points are in fact 28 billion light years apart. Since no signal can travel faster than the speed of light, points A and B should never have been able to communicate or exchange temperature with each other throughout the entire history of the universe. So why do they have such strangely identical temperatures? This is the horizon problem, also known as the puzzle of the universe's homogeneity. Next, let's talk about the flatness problem. Based on the latest cosmic map data, our universe appears to be absolutely flat. Even after 14 billion long years, the density of matter and the expansion rate of the universe have maintained a nearly perfect balance. Physicists have always longed to find a satisfactory explanation for why tiny initial deviations did not grow significantly to distort the universe's geometry. To help you visualize, in physics there are 3 simple models of the universe as follows. A closed universe. This is a universe with enough matter for gravity to overcome expansion, causing the universe to curve back on itself with a positive curvature, like the surface of a sphere. An open universe. A universe that expands forever because there is not enough matter to stop it, creating a distinctive shape like a saddle with negative curvature. A flat universe. This is a universe where the expansion slows down over time but never completely stops because matter and expansion are in perfect balance. In this space, there is absolutely no curvature, like a flat sheet of paper stretching to infinity. In 1980, astrophysicist Alan Guth proposed the inflation theory to definitively solve these 2 problems. According to this creative theory, the extremely rapid initial expansion flattened out any inherent curvature of the universe. You can imagine this as being similar to enlarging a tiny sphere to the enormous size of the Earth. In that case, the small patch of surface you are standing on would appear very flat, even though the entire sphere still has a curvature. Inflation also ingeniously solved the horizon problem by explaining that regions that were initially very close to each other had enough time to exchange temperatures before being scattered across the observable universe by the rapid expansion process. You can imagine this is like blowing up a balloon. Every point on the balloon's surface gets farther and farther apart, and a person standing at any point would feel as if they were at the very center of this great expansion. During this dramatic explosive period, the universe expanded by about 10 to the power of 78 times. Imagine that as the number 1 followed by 78 zeros, a number so large that our imagination can hardly grasp it. If someone wrote a tiny message on the surface of the balloon before inflating it, you would be able to read that message clearly after the balloon grew larger. Similarly, the process of inflation acted as a giant cosmic microscope of creation, magnifying tiny quantum fluctuations from a size of 10 to the minus 28 centimeters up to the vast scale of the cosmos. These primordial imprints are still permanently recorded in the distribution of galaxies and the different hot and cold regions of the cosmic microwave background radiation that we are quietly observing today. Today, the theory of inflation has become a solid cornerstone of our understanding of the dawn of the universe. For the 40 years since Alan Guth published his work, astronomers have been diligently delving deeper into the miraculous mechanism that allowed a tiny universe to explode so powerfully and suddenly. These dramatic phases occurred as the universe gradually cooled and its extreme energy levels decreased. This event marked the end of the grand unification of elementary particles and natural forces, while also witnessing the powerful emergence of the strong nuclear force. Some scientists have hypothesized that the decay of messenger particles carrying the strong electroweak force created an incredibly intense inflation field. This energy field was driven by a new type of messenger particle called the inflaton. This was the beginning of a new, immensely vast expansion. This enormous inflationary energy fueled the exponential expansion of the entire universe. This caused tiny quantum fluctuations to be instantly magnified to a much larger scale, forming the primordial cosmic structures. Those minuscule quantum fluctuations, like small ripples, gradually became vast regions of space filled with matter and energy, and eventually they became the precursors to the brilliant galaxy clusters and superclusters in our current universe. After all this rapid expansion, the universe finally cooled down and became emptier, causing the average energy level to drop by about 100,000 times. The exact reason why the inflation process stopped remains a mystery to scientists to this day. However, when it did, the inflation field and its particles began to decay, releasing radiation and elementary particles into the vast expanse. This process returned most of the energy to the universe in a significant process known as reheating. Imagine it as being similar to how water vapor in the atmosphere silently condenses into tiny droplets to form a fluffy cloud drifting in the sky. The formation of photons, binding particles, and quarks took place during this vibrant reheating process. But at that time, everything was still in a thick, hot state of plasma. Matter and antimatter particles began to collide and annihilate each other in a chaotic dance. However, for some profound reason that we still don't fully understand, this mutual annihilation resulted in a small excess of matter particles. It is this miraculous surplus of quarks that is the reason why today all the galaxies, stars, planets, and even us humans can exist and be present in this life. Furthermore, the grand unified theory also indicates that during this period, three additional fundamental forces, the electromagnetic force, the strong nuclear force, and the weak nuclear force, along with gravity, began to form, and then clearly separate. The universe, as we know it today, evolved as the four forces of nature, and the laws of physics officially came into effect. However, at this point, the universe was still too hot for quarks to combine to form protons and neutrons, although, in reality, these elementary particles had already begun to acquire mass through a special mechanism of creation. The reheating process ended at about 1/10,000,000th of a second. Thanks to this crucial milestone, matter could be fully created and merge into the vast expansion of the universe. The laws of nature gradually became more familiar and gentle to what our intellect can comprehend. We are now entering the third period of the universe, called the electroweak epoch, which occurred between 10 to the power of -36 seconds and 10 to the power of -12 seconds. Now, things begin to become clearer and gentler as we travel through the epochs of time. We can see how a tiny singularity could expand so rapidly to become the fascinating universe of today. The electroweak phase marks the beginning of the modern universe, because the four fundamental forces would become completely distinct from each other by the end of this period. In addition, we will witness the formation of the first particles that make up the matter we are familiar with, such as electrons, protons, and neutrons. When we think about these subatomic particles, did you know that there are many other types of particles and wondrous particle combinations that also exist? So, what exactly are these particles? Let's delve a little deeper into their nature. In our daily lives, as we leisurely drive a car, use a laptop, or cherish our smartphones, have you ever wondered about the long and magnificent history of the materials that make them up? Matter exists around us in four different forms: solid, liquid, gas, and plasma. In addition, another form of matter is the field, where we silently observe four different types of force fields governing all things. The electromagnetic field and the gravitational field are very familiar concepts, as we can easily see their effects in our daily environment. The other two types of fields are called nuclear fields, which occur in the microscopic world of atoms that are invisible to the naked eye. There are two types of nuclear fields, the weak and the strong, and they are always present with varying intensities to keep the physical world stable. The particle form of matter consists of two main groups of elementary particles. Elementary particles, also known as fundamental particles, are the smallest, most primordial building blocks of the entire vast universe. The main characteristic of elementary particles is that they have absolutely no internal structure. This means that researchers consider them as dimensionless points that do not occupy any space in reality. Take a quiet moment to imagine. In just one tiny cell, there are millions of different complex molecules. When we silently magnify one of these molecules, we will see individual atoms vibrating. To put it as simply as possible, there are about 40 trillion cells in a human body, and each tiny cell contains about 100 trillion atoms inside. However, atoms are not the final stop of this magical story. If we could continue to zoom in further, we would see clouds of electrons languidly lying on the outer shell of the atom. As you pass through the boundary of the atom, you will see vast, empty spaces before your eyes, like the space between the stars. But please don't stop there. If you continue to magnify further, the nucleus at the center of the atom will appear clearer than ever. However, the story of matter does not end at the nucleus. Looking deep inside the nucleus will reveal protons and neutrons bound tightly together by an invisible bond. These are the entities known as subatomic particles. Now, let's let our minds wander and zoom in once more on one of those protons. We will discover tiny particles constantly dancing vividly inside the proton. These are the quarks. We call these microscopic particles elementary or fundamental particles in the standard model of particle physics. There are 4 types of force-carrying particles and 12 matter particles in addition to the basic quarks. So, what helps us classify something as an elementary particle? If we look at a proton, it is composed of 3 quarks. So a proton is actually just a subatomic particle, not an elementary particle. An elementary particle is a type of particle that cannot be broken down into smaller parts because it has no internal structure. This implies that they are made of nothing at all. They are the final and smallest building blocks of the universe known to man. All materials in the universe are composed of matter particles called fermions and force-carrying particles called bosons. Leptons and quarks are the 2 important types of particles in the fermion group. Because leptons do not form groups and usually operate alone, they are classified as single particles. Like all other elementary particles, they lack an internal structure. There are a total of 6 different types of leptons, including the electron neutrino, the muon neutrino, the tau, and the tau neutrino. When these 6 types of particles are arranged by mass from heaviest to lightest, we have the tau and the tau neutrino as the heaviest in the group, while the electron and electron neutrino have the lowest mass. These leptons carry either a negative elementary charge or are neutral. The charge of the muon and the electron are both negative, equivalent to -1. In addition, the mysterious neutrinos have no charge at all. Not to be outdone by the leptons, quarks are another type of particle that are subtly grouped together. They also come in 6 different types with the most unique and poetic names in nuclear physics. The 6 types of quarks are up quark, down quark, charm quark, strange quark, top quark, and bottom quark. These quarks are also arranged in order from lightest to heaviest in terms of mass. In this group, the top quark is the heaviest, while the up quark is the lightest. In addition, antiparticles are also found among all types of quarks and leptons. They are particles with an opposite charge but an equivalent mass. As we've discussed, leptons are loners that prefer to be by themselves. In contrast, quarks only exist in groups and are very social, so they always combine to form composite particles. These composite particles are not considered fundamental because they are combinations of several different particles. Particles made of more than one quark are collectively called hadrons and are divided into 2 distinct types. First is the baryon group, which includes hyperons made of 3 quarks bound together. Second is the meson group, which includes particles composed of 2 particles, 1 quark and 1 antiquark. Bosons are the force-carrying particles, acting like a kind of cosmic glue that binds matter particles together into a unified whole. This group also has 4 main types: the graviton, which is governed by gravity; the photon, which is governed by the electromagnetic force; the gluon, controlled by the strong nuclear force; and finally, the W+, W-, and Z bosons, which are silently influenced by the weak nuclear force. Photons, or light particles, in this system have absolutely no mass, so they can travel freely through a vacuum at the speed of light, approximately 300,000 kilometers per second. However, just imagine if all fundamental particles were massless, our universe would be incredibly strange and different. In that case, a proton couldn't hold on to a massless electron to create a complete hydrogen atom. Furthermore, the absence of hydrogen atoms would mean no brilliant stars, no vast galaxies, and no life as we know it today. In about the first trillionth of a second after the beginning, elementary particles were inherently massless. However, something miraculous happened very quickly, right after the grand unification epoch, causing some particles to begin accumulating their own mass. But how could these particles acquire mass? To solve this mystery, in the 1960s, several brilliant physicists proposed a fascinating theory. They suggested that immediately after the Big Bang, a special force field was created that filled all of space. As particles interact with this field, they gain mass. Today, we call this the Higgs field. Our entire vast universe is filled with this invisible Higgs field. Through close contact with it, particles like the W and Z bosons acquire their mass. The stronger the interaction, the heavier the particle becomes. The difference between the massless photon and the massive W and Z bosons is precisely what we observe in nature today. The existence of the powerful Higgs field explains that miracle. Other force-carrying particles, like the photon and the gluon, remain massless, simply because they do not interact with the Higgs field at all. There are 2 ways we can detect the existence of a force field. An electromagnetic field can be detected by observing particles that interact directly with it. Another option is to create photons, the quantum particles closely associated with the electromagnetic field. but you cannot directly interact with the ever-present Higgs field to see it with your own eyes. To prove this field's existence, we have to create the Higgs boson, a quantum particle that appears in the Standard Model along with 16 other types of particles. This particle plays a crucial role in explaining the interactions and behavior of matter throughout the universe. Only by creating the Higgs boson through extremely high-energy particle collisions using giant accelerators like the Large Hadron Collider can we observe it. However, the Higgs boson decays instantly and is extremely unstable, so detecting it is an immense challenge. It immediately transforms into lighter particles. For example, it might decay into a pair of photons or 4 other particles that it leaves behind. To help you better understand this abstract idea, we can use a nice metaphor about water and swimmers. The water, in this example, represents the ever-present Higgs field. A fish with a very streamlined body interacts only gently with the water and can move through it very easily. In this case, the fish is like a very low-mass particle. Conversely, a person weighing about 80 kilograms can only walk slowly and with difficulty in the water. That person represents a massive particle that has become heavy due to its strong interactions with the water. In the mysterious microscopic world, the electron is the lightest matter particle we know of, while the top quark is the king of mass. It's nearly 350,000 times heavier than an electron, equivalent to the mass of an entire gold atom. It's important to emphasize that we shouldn't think that because the top quark is heavier, it must be larger in size. That's not the case at all. Scientists believe the electron and the top quark are exactly the same size. That's right, they share the same tiny dimensions. But the top quark is heavier simply because it interacts more with the Higgs field. The reality is that none of these particles could possess mass if the Higgs field didn't exist. Nowadays, the Higgs boson is mentioned in the press more often than the Higgs field. So how are these two concepts related? The smallest constituent components of the Higgs field are the Higgs bosons. Let's return to the water example once more. Everyone knows what water is. It's present all around us. If you're submerged in water, there are no empty spaces within it. We also know that water molecules are what make up that vast body of water. Similarly, the Higgs field is made up of countless individual Higgs bosons, just as water is made up of tiny water molecules. Peter Higgs and François Englert were honorably awarded the Nobel Prize in Physics in 2013 for their theoretical discovery of the mechanism related to this Higgs field. They skillfully established a theoretical framework that explains how particles acquire mass, giving it a solid place in the Standard Model and a crucial role in the evolution of the early universe. Always remember that bosons are not the particles that directly make up matter. Rather, they are the entities that carry force. This was a giant leap forward, a thorough preparation for physical matter to officially exist in the vast universe. It was the Higgs field that played the role of slowing down other particles and imparting mass to them. This is a concept that, while somewhat strange and hard to visualize, is the foundation that allows our universe to support mass. At the end of this era, the weak nuclear force and the electromagnetic force finally separated, which occurred at about 10 to the power of -12 seconds after the beginning. As the universe gradually cooled enough for all 4 fundamental forces to operate independently, the laws of nature that we describe in classical physics began to take clear shape. After the universe had cooled to about 10 million billion degrees and the 4 forces had separated, space reached a higher level of stability than before. We begin to witness the birth of a new era, the quark epoch. This was the first period defined by the true interactions of matter. It was here that we see the rapid and vibrant formation of quarks and antiquarks. These particles constantly collided with and annihilated each other whenever they met. Besides the normal matter that makes up you and me, there exists an opposing type of matter in the universe called antimatter. This special type of matter possesses an incredibly strange and powerful property. When antimatter interacts with normal matter, they immediately annihilate each other, creating a colossal and brilliant explosion of energy. To help you visualize this terrifying power, just 1 gram of antimatter coming into contact with 1 gram of normal matter would release an amount of energy equivalent to the atomic bomb that destroyed the city of Hiroshima in 1945. While combining matter and antimatter can create energy, the reverse is also completely true. Energy can also create matter and antimatter in equal amounts. Since antimatter was first discovered in 1931, the scientific evidence for its existence has grown ever stronger and has become widely accepted by physicists around the world. One of creation's greatest mysteries occurred when a tiny surplus of quarks began to accumulate. This was the result of a process that scientists call baryogenesis. According to this theory, for every 1 billion collisions between a quark and an antiquark, one lucky quark was not annihilated. It is thanks to this astonishingly small imbalance that mass and matter can exist in the universe today. Without that difference, the particles would have likely just collided and annihilated each other forever, leaving behind an empty, lonely universe filled only with pure, pervasive energy. However, how did matter and antimatter in the early universe come to have such a slight imbalance? Although scientists have proposed some insightful theories, we still can't say with absolute certainty. For example, in the 1960s, researchers discovered that the universe seems to slightly favor certain subatomic matter particles over their antimatter counterparts. We call these particles quarks. Additionally, scientists have another theory, because the difference between quarks and antiquarks doesn't seem sufficient to explain the existence of the entire visible universe. This involves neutrinos, extremely tiny and mysterious particles created during radioactive decay. An interesting fact is that the largest source of neutrinos closest to us is the human body itself. To determine whether neutrinos and antineutrinos behave differently, researchers are diligently building state-of-the-art particle accelerators and detectors. If these two types of particles behave differently, that could be the key to solving the mystery of our own existence. This would mean the universe was formed through a process called leptogenesis, meaning it was created from low-mass particles. The accumulation of quarks, along with the quiet presence of gluons, particles that carry the strong nuclear force, gave the universe its consistency, turning it into a dense medium of quarks and gluons. Eventually, the quark epoch came to a close, and a promising new chapter began, the hadron epoch. This era lasted from about 1 microsecond to 1 second after the Big Bang. At this time, the universe's temperature was about 1 trillion degrees, cool enough for quarks to combine and form hadrons. As we know, there are 2 main types of hadrons, baryons and mesons. The slight imbalance between matter and antimatter from the previous phase, also known as baryon asymmetry, led to the elimination of most antibaryons. As this epoch drew to a close, only the light and stable baryons, like protons and neutrons, were left. Due to the high density of leptons at that time, protons and neutrons constantly converted into each other under the influence of the weak nuclear force, creating a state of perpetual flux before the universe entered its next formative phases. As the vast universe gradually cooled, these dynamic nuclear conversion reactions began to slow down significantly. The result of this process was that for every 1 neutron, there were about 7 protons. Since a helium nucleus requires 2 protons and 2 neutrons to form, while a hydrogen nucleus needs only a single proton, this 7-to-1 ratio resulted in a massive excess of hydrogen compared to helium. This is the exact ratio we still observe in the universe today. To explain this clear abundance of helium, physicist George Gamow proposed a bold idea. He theorized that most of the helium in the universe was created right at the time of the early Big Bang, in a brief period faster than it takes to leisurely cook a chicken in your kitchen. He developed a profound theory that the universe was originally composed of a hot, dense mixture of particles. He called this primordial substance lelem, an ancient Greek word meaning the first matter of all things. From this mysterious substance, the first chemical elements began to form. He tasked Ralph Alpher, a dedicated PhD student at the time, with investigating the complex processes that could create heavier components from this formless matter. Together, George Gamow and Ralph Alpher cultivated the idea and published their famous scientific paper, The Origin of Chemical Elements. This paper became the gold standard for research into primordial nucleosynthesis and remains the firm foundation for understanding how the extreme heat of the early universe could forge simple hydrogen into helium. This process took place through the creation of deuterium, with protium, the lightest form of hydrogen, containing just a single proton as an intermediate. These hydrogen nuclei had been present from the moment quarks first bound together to form protons. It's important to remember that electrically neutral hydrogen atoms, the state where a proton and an electron are paired, could not yet form during this intensely hot period. By then, the spherical space around the initial point had expanded into the observable universe, with a vast radius of about 10 light-years. About 10 seconds after the Big Bang, the temperature had dropped enough for some deuterium nuclei, each containing one proton and one neutron, to begin forming. However, these deuterium nuclei were still unable to reach a stable state in that sweltering cosmic environment. The density and energy of particles was still so high that if one of these first nuclei was struck by a stray photon, it would immediately be blasted apart. Physicists call this challenging phenomenon the deuterium bottleneck. Until this bottleneck was passed, nucleosynthesis could not proceed beyond the fusion of one proton and one neutron. It took another 300 long seconds for the cosmic temperature to drop to a level where deuterium became stable, allowing other elements to begin forming. First, deuterium nuclei were able to fuse with individual protons under the immense pressure of the entire universe at that time. The result was the helium-3 nucleus, a brand new and stable element, which appeared in space for the very first time. After this point, a more common and familiar form of helium, helium-4, consisting of 2 protons and 2 neutrons, began to form in great quantities. Helium-4 is an incredibly stable element, and one of the most resilient nuclear structures known to humanity. It was this property, combined with the extreme conditions of the first few hundred seconds, that caused most of the free protons in the early universe to be absorbed into helium nuclei, remaining stable without decaying further. Even after 13.8 billion long years since that powerful explosion, through the birth and death of countless stars, our universe is still composed of about 23% helium. This precious observation alone provides compelling evidence for Ralph Alpher's theory. It's also proof that the initial conditions of the universe seem to have been arranged by a random yet incredibly precise and delicate hand. We know that if the proton-to-neutron ratio had been only slightly different, most of the ordinary matter in the universe would have resolved into chargeless neutrons and inert helium. Likewise, if matter at the time of the Big Bang had been denser, even more helium would have been created. A helium-dominated universe would have no complex chemistry, leading to a bleak and static future. No brilliant galaxies, no warm stars, and no us here to admire it. Fortunately for us, that is not what happened. Even as many hadrons settled into helium nuclei, the universe was still brimming with energy for subsequent fusion reactions. A quiet and fascinating race was on to create as many new elements as possible before the energy of the surrounding environment fell too low for the reactions to continue. After the universe's first 20 minutes, or about 1,200 seconds of intense nucleosynthesis, nature's giant reactor finally slowed to a halt. The environment was now too cool for any more nuclei to form, even though it was still incredibly hot and hostile by human standards. At this moment, the universe contained just 4 primordial elements: hydrogen, helium, lithium, and beryllium. Of these, only the first 3 were stable enough to see the birth of the first stars and become the primary fuel for the story of the other 98 elements in the periodic table we know today. This selectivity was because beryllium nuclei are inherently unstable. At that moment, the universe was a brilliant sea of energy, where for every single particle of matter, there were about 1 billion photons surrounding it, and for every helium nucleus, there were about 12 hydrogen nuclei. With these pure, fundamental components, the grand stage was set for the formation of all things. Even the isotopes like deuterium and tritium that scientists fused in California in 2022 were, in fact, first forged in the brilliant heat of the nascent universe 13.8 billion years ago. The fusion and fission of particles to create the primordial mixture of hydrogen, helium, and a small amount of lithium officially marked the end of the nucleosynthesis epoch. This process set the stage for the formation of the brilliant stars to come. From an initial size smaller than a grapefruit, the universe had quietly expanded to a radius of about 300,000 light-years by the end of this phase. Today, our universe has become immensely larger and more vast due to its continuous, unceasing expansion. As the universe expanded, it cooled, and its temperature gradually dropped from about 1 billion Kelvin down to 3,000 Kelvin during this period. When nucleosynthesis ceased, we began to see nuclei combine with other particles to form atoms, and further on, witness the birth of galaxies and brilliant stars. After the period of nucleosynthesis, we entered the era of nuclei. The biggest difference is that this stage marked the end of nuclear fusion. The universe was still growing every day as it expanded, although the pace had slowed down and become more leisurely compared to the previous era. Our universe at this time had become a colossal space filled with fully ionized particles. You can sense that as the universe grew older, it expanded, and its internal pressure continuously dropped. As the volume increases, the pressure decreases. This is a natural and harmonious inverse relationship. Therefore, nuclei no longer collided violently enough to fuse with each other. The universe was still just a scorching plasma ball of charged particles. During this time, fusion reactions could not continue because the temperature was too low, yet it was still high enough to keep all the atoms in an ionized state, meaning electrons were still roaming free and could not yet combine with nuclei. Until about 500,000 years after the Big Bang, particles of light were continuously scattered by the free electrons that filled the universe. They couldn't travel far because they would collide with other charged particles after moving just a short distance. This created an equilibrium state that kept light trapped and unable to escape. The era of nuclei produced a great deal of light, but we couldn't see anything because the density of the universe was extremely high. The universe at this time was like a thick, opaque, and mysterious fog, not allowing any ray of light to penetrate and illuminate the space. The era of nuclei lasted from the 3rd minute up to 500,000 years after the Big Bang. After that 500,000-year mark, the universe finally cooled down to about 3,000 Kelvin. At this magical moment, hydrogen and helium nuclei began to capture free electrons to form the first neutral atoms. Once the electrons settled into place within the atomic shells, particles of light were no longer scattered or obstructed. most of the gas in the universe at this time became pristinely transparent, allowing the particles of light to finally escape the plasma fog and begin their journey across the vast universe. These ancient and enduring particles of light are what we now call the cosmic microwave background radiation. When we gaze into the deep night sky, we cannot see further back in time than this 500,000-year mark. That was the last time light scattered before it truly became free. Before that moment, all we could see was a hot, opaque, and mysterious surface of a universe gestating wonders. Now, let's explore together what really happened to the atomic nuclei, electrons, and light as we step into the next stage of the history of everything. This is the era of atoms. This phase officially began when light decoupled from matter and nuclei began the process of fully combining with electrons. After stable atoms were formed, matter no longer had any influence or obstructive effect on light. The particles of light and the neutral atoms together created a truly vast and open cosmic space. Throughout this transformative period, the temperature of the entire universe fluctuated from 3,000 degrees down to a mere 60 degrees Kelvin. Our universe suddenly became transparent thanks to the drop in temperature and the decoupling of light. This meant that electromagnetic radiation, including brilliant light, could now move freely throughout the vast space with more freedom than ever before. To help you easily visualize this marvelous process, try to imagine a parking lot packed with crowded vehicles. Our atomic nuclei are like drivers standing outside, while the free electrons are the pedestrians weaving between the crowded rows of cars. Imagine you're trying to cross through that traffic. The cars and pedestrians are like the nuclei and free electrons, constantly colliding with you and pushing you in every direction, making it impossible for you to get far. However, when people get inside their cars, that is, when the electrons have fully combined with the nuclei to form stable atoms, the space suddenly becomes empty and vast. Now, you can leisurely walk through it all without getting stuck or scattered by any obstruction. This magical stage in the evolution of the universe is formally called the period of recombination by scientists. This is when nuclei and electrons first found each other to create the first stable atoms. This stage also goes by another name, the period of decoupling, because it was the glorious moment when light could finally separate itself from matter to travel freely across the infinite space. The reason we observe the cosmic microwave background radiation today as low-energy light is simply because the continuous expansion of the universe has stretched the light particles, causing them to be shifted toward the red end of the light spectrum. In fact, the original energy of these light particles was in the ultraviolet region, with very short and powerful wavelengths. Since its discovery, humanity's cosmic background explorer satellites have meticulously measured it and found that it perfectly matches the spectrum of an ideal black body at a temperature of 2.73 Kelvin. This radiation emanates uniformly from all directions in space, serving as solid and vivid evidence that we have understood the universe from at least 500,000 years after the Big Bang. However, the cosmic microwave background also reveals to us an incredibly serene and silent early universe, where the structure and temperature had almost no significant changes, with only gentle fluctuations of a few degrees compared to today. It was a very different environment, with no brilliant galaxies and not a single star shining in the sky. We only see an astonishing uniformity. Astronomers affectionately and mysteriously call this period the Dark Ages. The universe continued to expand and cool after recombination, ushering in a long, dark era. The dazzling light of the Big Bang had now gradually shifted into the invisible infrared region of the spectrum. This dark age lasted for hundreds of millions of years, beginning around 400,000 years after the Big Bang. This was the final period when the universe had a truly empty and silent appearance. There were no planets, no warm sun, no Milky Way, and no life present yet. Everything was just a hazy mist of hydrogen atoms created from the Big Bang, drifting lazily in the vast, deep darkness. Today, the world's most advanced telescopes are tirelessly and persistently searching for faint traces of this primordial hydrogen gas, also known as neutral hydrogen, in order to precisely determine the moment the Dark Ages ended and the first galaxies began to take shape. Throughout these ancient cosmic epics we have journeyed through, you have witnessed the miraculous emergence from a tiny singularity until it became a colossal space filled with atoms. Now, let's explore the era of galaxies together to understand how the universe reached its current brilliant state. Under the silent yet powerful guidance of gravity, matter began to clump together to form the very first galaxies. This event marked the greatest transformation in the structural evolution of the entire vast universe. These first galaxies completely changed the intergalactic medium, transforming it from a quiet, neutral state to a vibrant, ionized one. This miraculous transformation was made possible by the brilliant first and second generations of stars, along with powerful energy sources from microquasars or X-ray emitting binary star systems. This process is called the era of reionization by scientists. During this phase, star formation was incredibly intense. Stars began to emit powerful streams of radiation, causing neutral hydrogen atoms to be split once again into free protons and electrons. The abundant energy from early stars, young galaxies, and brilliant quasars with giant black holes at their centers joined forces to reionize the vast expanse of hydrogen gas. Ionization is the process where energy from a star strips electrons from surrounding gas atoms, causing them to shimmer and glow in the void. Since this was the second time the gas clouds were excited and heated since the Big Bang, this period is named reionization. Thanks to this magnificent combination of energy, light was able to travel farther into the vast space than at any time before. Model, perhaps the most compelling and evocative question in astrophysics today, is understanding the early formation of stars. This will help us thoroughly comprehend how the first galaxies were created from nothing. The James Webb Space Telescope was launched into the sky with the noble mission of finding the answer to that very question. With its superior infrared observation capabilities, it allows us to see through strongly redshifted objects, which are the distant galaxies beckoning from the dawn of the universe. Through the flow of time, galaxies were gradually pulled closer together by the silent yet persistent force of gravity, forming galaxy clusters and enormous superclusters. The tiny differences in density in the initial microwave radiation were the precious seeds from which stars grew and exploded, creating the magnificent diversity of the cosmos. By this time, our universe had expanded to a diameter of up to 93 billion light-years. The temperature also gradually decreased from 60 degrees to the extremely cold level of 2.73 Kelvin. The universe is still constantly evolving, and the reality is that we are living right in the era of galaxies. A mysterious component called dark matter seems to be present everywhere, surrounding the stars we can see. Galaxies frequently collide with each other because their dark matter halos make them much larger than their splendid appearance suggests. The collision and merging of small galaxies have led to their consolidation to form enormous and majestic galaxies. The two fundamental components that make up the entire universe are matter and energy. However, an astonishing truth is that the majority of matter in the universe is completely invisible, and the origin of most of its energy remains a profound mystery. This is an immense challenge. If most of the universe is invisible, how can we possibly study it? Scientists are still at the forefront, working tirelessly on the journey to find answers about dark energy and dark matter. With increasingly sophisticated and precise observation techniques, the distribution of dark matter in galaxy clusters, such as the Bullet Cluster, has been mapped in very high detail with the help of NASA's Chandra X-ray Observatory. These observations reveal brilliantly heated gas regions as the galaxy clusters collide and slow down. But the dark matter remains quietly separate and completely unaffected by the violent collision. One theory suggests that some dark matter particles can be annihilated in powerful bursts of radiation. These faint signs are being closely monitored by modern telescope systems in Arizona, which are capable of detecting extremely high-energy gamma rays. By comparing actual observations with computer simulations, researchers are learning how dark energy and gravity have contended with each other throughout the long history of the universe. Thanks to the technique of gravitational lensing, we can measure the degree to which light bends as it passes by celestial objects to accurately calculate the amount of dark matter present. When the calculated mass is much greater than the directly observed mass, we know for certain that dark matter must be hiding there. Journeying back in time about 4.5 billion years ago, our solar system began to form from a dense interstellar cloud of gas and dust. This cloud collapsed, possibly due to a shockwave from a nearby supernova explosion. As this dust cloud collapsed, it formed a solar nebula, a spinning disk with matter densely concentrated at the center to create our warm Sunday. The planets and moons also gradually formed from this disk of gas and dust in the same miraculous way. The pull of gravity patiently drew dust particles together, forming small clumps of rock, which then gradually grew into planetesimals hundreds of kilometers in diameter. After these protoplanets collided and bonded together over millions of years, our beloved Earth was officially born. Today, matter in the universe has completely dominated over radiation. The components that make up atoms, such as protons, neutrons, and electrons, along with mysterious dark matter, have given shape and stability to our world. Although the cosmic microwave background radiation is very faint now, it still contains more energy than all the known stars and galaxies combined. This is because even though stars are intense sources of light, they occupy an incredibly small and sparse fraction of the vast, endless space. In physical terms, our universe appears to be an incredibly miraculous and perfect existence. If the natural constants were to change just slightly, life, planets, and everything beautiful we see would never have come into being. This brilliant universe is an exquisite symphony woven from the laws of physics and the fundamental forces of creation. It is not a random collection of matter, but a masterpiece of absolute precision. As we continue to explore the vastness of space, we cannot help but be amazed by its elegance and harmony. Perhaps the delicate balance that sustains our existence still holds profound secrets yet to be fully revealed. A great cosmic symphony is still waiting for us to decipher its every rising and falling note. Therefore, I want to tell you that you can achieve anything you desire, as long as you know how to listen to the pulse and connect your soul with the vast universe. All you need to do right now is let go of the worries of a long day, feel the wonderful flow of life, and the universe will astonish you with the most beautiful miracles. Let's close our eyes together, look up at the starry sky in our minds, embrace the mysteries of space, and enjoy the inspiring perfection of this universe. I wish you a very good, deep sleep and beautiful dreams among the sparkling stars.